participants. Thank you for joining the webinar organized by Quvae Research and Publications. Our journey, milestones we are proud of. We have conducted over 40 webinars and workshops globally, hosted 30 webinars exclusively in Thai. Today, we have more than 5,000 active Quvae members from various countries. We partner with top universities, research institutions, and academic bodies to support our mission. Quvae webinars and workshops, an engaging learning platform. We cover topics like research writing and journal selection, with international experts offering valuable insights. Our workshops are tailored to meet the academic needs of different regions. Webinars in Thailand, tailored for the Thai academic community, covering topics like manuscript writing and publication strategies, with a strong member base fostering collaboration. Our vision is to support researchers in achieving excellence, bridging gaps in the publication process and quality services, and fostering a global academic community of collaboration. Get in touch with Quvae for proofreading, editing, and Scopus journal support. Follow us for updates on webinars and workshops. Visit our website or contact us for more information. Thank you for watching.
यहाँ पर है
क्या
जहाँ कहीं वापस चले गए थे वहां से रहा
इतना ये कितने का दिया चाय
3.39 ले लीजिए
रख लेते
आना चाहिए आपको ही
Greetings to all the
Kyo?
participants present here. On behalf of Quvae Research and Publications, I would like to welcome you all for the workshop on Mastering Regression Analysis, a step-by-step guide with SPSS. To start with, let me give you a brief information about Quvae Research and Publication.
मैंने गर्म किया था
ठंडा भी तो हो गया
हाँ
दूरी है ना
हाँ दूध ये है क्या दूध इसमें
Quvae serves as a platform to publish research articles in prominent journals and conferences proceedings. We assist authors in publishing their research findings in high impact factor journals, promoting their work, enhancing their reputation, and building a strong scientific profile. Among several indexing databases, Scopus is one of the most preferred for publishing articles. The wide recognition and impact of these journals make them highly valued in their academic career. We have recently collaborated with the Scopus Q1 journal, FN1000 Research, published by Taylor and Francis. The authors can now easily submit their articles through a partner gateway with FN1000. FN1000 Research is an open research publishing platform for scientists, scholars, and clinicians that offers rapid publication of articles and other research outputs without editorial bias. All articles benefits from transparent peer review and editorial guidance on making all source data openly available. Now, I would like to welcome our speaker, Dr. Nurul Noor Hazmi, who is a biostatistic lecturer at Mahasa University's Faculty of Dentistry, holds an MSc in Medical Statistics from the University Science Malaysia. She commenced a career at the Center of Excellence for Research in AIDS at the University of Malaya, serving as data manager, medical statistician for 4 years. Trained at Singapore General Hospital, she introduced the Research Electronic Data Capture (REDCap) system at the University of Malaya in 2015. The initiative has had a significant impact with REDCap, now implemented in 12 Malaysian institutions, including the Ministry of Health, showcasing her influence in advancing research methodologies and data management. Beyond her research, she actively educates undergraduate and postgraduate students specializing in research methodology and biostatistics.
S.
Our involvement extends to
S
various
करे.
webinars and workshops, demonstrating a dedication to disseminating knowledge beyond traditional classrooms. Now, once again, I would like to welcome you, Doctor. You may start now.
Assalamualaikum and a very good morning. Thank you very much for the introduction. Can you hear me?
Yes, Doctor.
Okay, thank you.
Yes.
Thank you very much for the introduction. My name is Jannah. I'm a senior lecturer in research methodology and also biostatistics from Faculty of Dentistry, Masa University, located in Malaysia.
अब देखो
Okay. I think we have to
वर्कशॉप चल रहा
mute.
है चला
Can someone mute the person? I can. Okay. May I know where you are from?
Doctor, you can start the webinar now.
Okay. Okay, thank you very much. Okay. May I know where you are from?
Dear Doctor, we can discuss it about later. Now we can start a workshop.
Okay, thank you. Thank you very much. Okay, Thailand, USA, Turkey. Okay, thank you very much for participating in this 3 hours workshop on regression analysis. Okay, for your information, today we are going to focus on multiple linear regression and also multiple logistic regression. So we're going to do hands-on by using SPSS. So it's a statistical software. I hope all of you already have SPSS installed in your laptop or your PC because today we're going to do hands-on. Okay, whenever I did my webinar or workshop, I always ask my participant to do it together with me because statistical analysis is all about practicing. If you don't do it, you will not be able to understand it very well. All right, so for information, I'm using SPSS version 27. So if you're using version 29 or 30, shouldn't be a problem. Yes, it's not free, I know, but you can try downloading the trial version first if it's okay with you. So you can use it. I think the trial version can last about 1 month, so you can try to download it for the sake of this workshop. All right, thank you so much. I already sent out 3 lecture handouts: Introduction to Regression Analysis, Multiple Linear Regression, and also Multiple Logistic Regression. And I also sent 2 data sets that we're going to use throughout the session. So if you're using version 29 or 30, there will be a slightly different than mine because I'm using version 27. All right, but don't worry about it. Okay, first I'm going to start with introducing you to regression analysis. So in this lecture, okay, I'm going to explain to you the basic about regression analysis. And then I'm going to focus on simple linear regression so that when we proceed to multiple linear regression later on, you have an idea what is simple linear regression in the first place. All right. Okay, first I'm going to introduce you to regression analysis. Have you ever heard about the word machine learning? So machine learning is actually a part of artificial intelligence. So it involves algorithm and also statistical model that help you to identify and also make prediction about based on the data that we have. So same goes with regression modeling because regression modeling is a part of machine learning. So we use it in our everyday life. We use it to predict changes in the stock market, to predict forecast. We use it in education and learning, healthcare, and so on. So the concept of regression modeling was introduced by the famous French mathematician back in 1805, Adrien Marie Legendre. So back then, so since then, regression modeling has remained fundamental in applied statistics. So the reason we use regression analysis is because we want to estimate, we want to see the relationship between dependent variable, which is the outcome of the study, and also one or more independent variable. We call it predictor variable. Okay, dependent variable is the outcome of the study. Independent variable is the risk factor, is the variable that affects the outcome of the study. When you talk to someone about your research project, about the result, about the findings of your study, you are actually talking about the outcome, which is the dependent variable. Okay, I'm going to explain to you the differences between independent and also dependent variable. So you have to understand properly, because if you don't understand it, you will not be able to choose the right statistical analysis for your research project. So independent variable is the variable that is changed. Okay, dependent variable is the variable affected by the change. For example, we have amount of water as the independent variable. We have size of plant, number of leaves, survival of the plant as independent variable. So in this scenario, in this context, we want to see whether amount of water affects the size of plant, whether amount of water affects the number of leaves, whether amount of water affects the survival of the plant. So the independent variable is the variable that affects the dependent variable, which is the outcome of the study. Okay, I hope you can understand the differences between independent and also dependent variable. Okay, the reason we use regression analysis is because we want to see the relationship between independent and also dependent variable. We want to see the linear relationship between these two, and then at the same time, the most important thing is that we want to predict the outcome. We want to predict the future based on the independent variable that we have. Okay, for example here, the outcome of the study is the blood pressure. Okay, this is the dependent variable. So we have two independent variables. We have age and also diet plan. So here we want to see whether age affects blood pressure, whether diet plan affects blood pressure. So blood pressure is the outcome. Okay, second example is, okay, our dependent variable is the length of hospital stay. Okay, the length of hospital stay. So we have three independent variables that consist of age, treatment methods, and also severity of illness. So here we want to see whether age affects the duration of hospitalization, whether treatment methods affects the duration of hospitalization, whether severity of illness will affect the duration of hospitalization. So this is the outcome. This is the independent variable. Okay, this is the basic, we call it basic regression model that consists of single predictor, one outcome variable, and then one coefficient. Y equal to B0 plus B1 x1 plus error, where Y is actually the outcome, which is the dependent variable. B0 is the intercept of the regression line. B1 here is the slope of the line, which is the regression coefficient for independent variable, and x1 here is the independent variable, and error is the residual. Okay, error here is the residual. I'm going to explain further details about this equation later on. Okay, this is our regression. This is our scatter plot. This is the scatter plot between length of baby and also maternal height. This is y-axis. This is x-axis. Okay, this is y-axis. This is x-axis. So y-axis here is the length of baby, and then x-axis here is the maternal height. So remember y, okay. So y here is the outcome, which is the dependent variable. So y here is the outcome. So this is our outcome, our dependent variable. This is our independent variable. So the blue dot that you can see here is actually the data, the actual data. The line here is the regression line, or we call it the prediction line. Okay, this is the regression line. Okay, for example, let's say if you want to estimate the length of baby based on the mother's height. Let's say the mother's height is 155 cm. So we will predict the length of baby will be 50 cm. If mother's height is 175 cm and the length of baby will be 54 cm. So this is, we call it prediction line or regression line. Okay, so the blue dot that you can see here is the actual data. Okay, this is the actual data. So the value that falls in on the prediction line here or the regression line here, we call it predicted value. So the error, okay, coming from this equation, error equal to residual. So error equal to residual, okay, error is actually residual. Is the difference between actual value, the blue dot here, and predicted value. Okay, error or residual equal to actual value minus predicted value. I highlight this is because when we do regression analysis, you always encounter the word residual. So later on, you will find a lot the word residual. So please remember this, residual or error equal to actual value minus predicted value. Okay, so now let's look at simple linear regression. Simple linear regression is used if you want to estimate the relationship between two quantitative variables. So what is quantitative? Quantitative is numerical. Any variable that concern with numbers. For example, age, weight, height, cholesterol level, blood pressure. So all of these are numerical variable. So as long as your dependent variable and your independent variable numerical, you can use simple linear regression. But the problem is many people always confuse with Pearson correlation. Okay, Pearson correlation also uses the same concept between two quantitative variables. The only difference is that in Pearson correlation, we are more interested to see the relationship and strength between the variable. But in simple linear regression, we are interested in making prediction. You can see the relationship, you can see the strength, and at the same time, you can make prediction. So that's the difference between simple linear regression and Pearson correlation. But let's say you just want to see the relationship between these two, you just want to see the strength, then go ahead use Pearson correlation. Okay, so when to apply simple linear regression, first you want to see the relationship between two quantitative variables. You want to see the strength between these two, but the most important thing, you want to make the prediction of the outcome based on the independent variable that you have. Okay, so let's see the differences between simple linear regression and also multiple linear regression. In simple linear regression, it only involves one independent variable only. So if you have one independent variable only, then you can use simple linear regression, but your dependent variable must be numerical, your independent variable must be numerical as well. For example, in this case, our dependent variable is length of baby, which is the outcome of the study. And then independent variable is the mother's height. So we want to see the relationship between these two variables. Okay, the second one is the multiple linear regression. So the difference between multiple linear regression and simple linear regression is that in multiple linear regression, we have more than one independent variable. And your independent variable must be numerical. Okay, all independent variable must be numerical. Dependent variable is numerical, for example, length of baby, and then you have set of independent variable, for example, mother's height, weight, and also age. So this variable must be numerical. Okay, I repeat again, in simple linear, we have only one independent variable. In multiple linear, you can have more than one independent variable, but all variables must be numerical. Okay, what happens if your independent variable combination of numerical and categorical, or you only have categorical variables only? That one, we call it general linear regression. So the dependent is numerical but the independent variable is a combination between numerical and categorical or categorical variable only. But I won't cover general linear regression for today's session. I will only cover simple linear, multiple linear, and also multiple logistic regression. Okay, this is the regression equation. Y equal to A plus Bx. So it's actually similar with Y equal to B0 plus B1 x1. So it's the same thing. Do not confuse between these two equations. So it's the same thing. So Y is the outcome. Okay, Y is the outcome, is the dependent variable. So A here is the intercept. So this is the intercept. Okay, B here is the slope, is the slope of the line. And then X is the independent variable. So Y equal to A plus Bx is similar with Y equal to B0 plus B1 x1. When we do regression analysis, you will always find the word coefficient of determination or R squared. Okay, R squared provides us how well future outcomes are likely to be predicted by the model. So I'll explain about R squared further later on. So the value of R squared always positive. So it range from 0 to 1. Okay, so in simple linear regression, we have 4 assumptions altogether. We have 4 assumptions altogether. You can use the word keyword line. So L stands for linearity. So the relationship between independent and also dependent variable must be linear. Okay. Categorical data means that I receive a lot of direct message actually. So I will I will reply to you one by one later on. Okay, categorical, you mean categorical data. So for categorical data or categorical variable, is a variable that consists of categories only. For example, gender. Okay, gender, we have category male and female. So that one, we call it categorical variable. Another word may be another variable, for example, race. We have Malay, Chinese, and Indian. So we have 3 categories. So this is, we call it categorical variable. For simple linear regression, yes, it's up to you. So it depends on your research objective whether you want to use simple linear regression or Pearson correlation or not. If you want to see the relationship between dependent and also independent variable only, you just want to see the strength between these two, you can just use Pearson correlation. But if you want to make prediction, you can use simple linear regression. So it doesn't matter which one, so it depends on you. It's your choice, right? Okay, for assumption, the first one that you have to check is the linearity. So you have to make sure the relationship between independent and dependent variable must be linear. The second one is independent observation. For independent observation, you don't have to check during analysis. So you just have to make sure you don't collect the same data during data collection. And then the next one, the residual should be approximately normally distributed. So remember, residual equal to error is a difference between actual data and predicted actual and also predicted value. The residual should be approximately normally distributed. And the last one, homozygosity, we call it equivariances. We want to make sure the spread of the residual, okay, the spread of the residual is consistent. Okay, this is the list of the assumption that you have to check. So how to check for every of the assumption? So the first one for linearity, okay, relationship between the independent and dependent variable is linear. So how to do this? You have to create a scatter plot between independent and also dependent variable. The second one, independent observation. So you don't have to do during the analysis stage. And the next one, residual should be approximately normally distributed. So this one, you have to create histogram and then see whether there is a bell-shaped curve or not. So if there is a bell-shaped curve, it means that the residual should be approximately normally distributed. And then the last one, you have to check for homozygosity, or we call it equivariances. So here we have to check the scatter plot between the residual and also predicted values. So we use this keyword SPYR. So x-axis you put predicted, y-axis you put residual. So I'm going to show you later on. Okay, now please open dataset birth weight. I hope all of you have dataset. Okay, please open dataset birth weight. I hope all the participants today know how to use SPSS, because actually regression analysis is more on intermediate, and also we call it intermediate statistical analysis. Means you already know the basics in statistical analysis. Okay, when you open this dataset, you can see we have a lot of variable. Okay, the first row that you can see here, this we call it variable, and then the rest is the dataset. So we have, for this, we have 42 data altogether. So you go to variable view, so you can see the list of variables that we have. So here we have 15 variables altogether. So the first one, ID, is not a variable, so it's just the ID. It's the number of the case that we have, okay, the number of the data. So total, we have 15 variables altogether, all right? Okay, this dataset contains information on newborn babies and their parents. So here we want to see, is there any relationship between maternal height and also length of baby? So a study was conducted to determine the relationship between mother's height and also the length of baby, with the researcher aiming to forecast the baby's length using the mother's height as a predictor. Okay, so first, you look at our objective. We have the word forecast, so means you want to make prediction. Okay, you want to make the prediction. So the first thing that you have to do is that you have to list down all the variables that you have. This is always, I always ask my students, participants, whenever you want to choose the right statistical test for your research, you have to go to your research objective and then list down all the variables that you have in every objective. The variable must be available in your dataset. All right. So the first variable that we have here, we have baby's length of baby, and then we also have mother's height. You have to make sure you check with your dataset whether these variables are actually available or not. So here we have, okay, for mother's height, we're going to use M height. So this is mother's height data. All right. For length of baby, we're going to use length. So this is length of baby's data. So list down all the variable and then identify the type of variable. So the length of baby here is numerical, is a numerical. You can see here is numerical. So look at mother's height. Okay, mother's height also numerical. So both variables are numerical variable. So the right statistical analysis that we can use in this scenario is simple linear regression. Why? Because we want to make a prediction. And the second one, both variables are numerical variable. Okay, I hope you can understand. So in this one, mother's height and also length of baby. So which variable that you think, okay, is dependent variable? Mother's height or length of baby is independent variable. Okay, so between mother's height and length of baby, we want to make the prediction. Okay, we want to make the prediction baby's length. So means the length of baby or baby's length is the outcome of the study or dependent variable. So mother's height is the independent variable. So now let's do simple linear regression. Our null hypothesis is there is no relationship between mother's height and the length of baby. Alternative is the opposite of hypothesis, is opposite of null hypothesis. There is a relationship between mother's height and also length of baby. And then step number 2, let's run simple linear regression. Okay, let's do it together. If you have any confusion, maybe you can let me know. I will try my best to answer you because we have a lot of participants actually for the hands-on session, so it's not easy for me to help every one of you, but I will try my best. All right. So to run simple linear regression, so go to analyze, and then go to regression, and then go to linear. Okay, go to linear. Here we have dependent and also independent. Okay, so we have dependent and also independent. So our dependent variable here is the length of baby because we want to make the prediction of the length of baby. So enter length of baby into dependent. Okay, enter length of baby into dependent, and then enter maternal height into independent. Okay, maternal height into independent. Right? And then go to statistics. Go to statistics. Under regression coefficient, click confidence interval. Okay. Continue. And then click OK. So we have another window display. We call it output window. So all the statistical analysis will be displayed in this window. You can even save this window if you want. So when you see, we have a lot of tables here, but the most important table that you have to know is the coefficient table. So you can go to the last table. Okay, you can go to the last table. So this is coefficient table. Okay, you see, this is the word constant. We have constant, we have maternal height. Okay, so this is the regression coefficient. This is regression coefficient. Okay, go back to the, okay. Okay, y equal to b naught plus b1 x1. So y is the outcome, which is the dependent variable. So y is the length of baby. B naught here is the value of regression coefficient for the constant, which is 15.33 plus B1 is a value of regression coefficient for the mother's height, which is 0.22, and the x1 here is the mother's height. Okay, in the coefficient table, the most thing that you have to know is the p-value. Okay, the p-value of the independent variable. So you look at the p-value. So this is the p-value, the significant value. So this is the p-value. So look at the p-value of the mother's height, which is 0.001. If the p-value is less than 0.05, so it means that there is significant relationship, or there is statistically significant between mother's height and also the length of baby. So remember, you can only come out with regression equation y equal to b naught plus b1 x1 if the p-value here is significant. If p-value here is not significant, then you cannot create the regression equation, or we call it regression model. So it's the same thing. Regression model equal to regression equation. Okay, so we have here model summary. Okay, model summary, so you look at R square. So this is coefficient of determination. Okay, this is coefficient of determination. So the value here is always positive. So it ranges from 0 to 1. So 0.235, you can convert to percentage. 23.5% of the variation in the length of baby is explained by mother's height. So R squared equal to 0.235. So it's up to you whether you want to report this in your manuscript or report or not. So we also have ANOVA table. So ANOVA table indicate whether regression model predict the dependent variable significantly well or not, but this one only overall. It's not one by one. Let's say if you have more than one independent variable later on for multiple linear regression, so this ANOVA table can only predict the dependent variable significantly well or not generally, okay, not one by one. So here, if p-value is less than 0.05, so indicate that the regression model statistically significantly predicts the outcome variable. So this is how we present the result for simple linear regression. Okay, for information, you cannot copy the table that you get from SPSS and then put in your manuscript or your thesis. So you have to create another table for it because we don't need all the information that we have in SPSS. So we only need certain information. For example, for simple linear regression, we are only interested with P is the regression coefficient, okay, 0.22, and then 95% confident interval, which can be taken from here, 0.09 and 0.35, and then p-value, okay? The most important thing is the p-value, whether it is significant or not significant. So after that, once you come up with the regression model, right? You already have your own model. You have one maternal height found to be statistically significant. Now you want to check the assumption. The reason we check the assumption is because we want to see whether the regression model that we come up with can actually predict the outcome or not, whether it's actually good or not to predict the outcome. All right, so we have 4 assumptions. Okay, we have 4 assumptions, but we only have 3 assumptions to be checked during analysis process. For independent observation, you don't have to check. You just have to apply during data collection part stage. So the first thing that you have to check is linearity. Relationship between independent and dependent variable must be linear. So how to do this? You have to create a scatter plot between independent and also dependent variable. Okay, the next one is homoscedasticity, or we call it equivariances. So here we want to make sure the spread of the residual is consistent. So how to do it? We create a scatter plot between residual and also predicted values. We use rule of thumb SPYR, where x-axis we put predicted, y-axis residual, and the last one, residual, should be approximately normally distributed. So how to do it? We have to create a histogram and then we see whether there is bell-shaped curve or not. If there is bell-shaped curve, it means that the residual is normally distributed. Okay, first, we are going to check for linearity. So how to do it? We are going to create a scatter plot between independent and also dependent variable. So now go to graph, okay, legacy dialogues, and then go to scatter or dot. Okay, so now please click define. I can see many people DM me right now, but I will reply later on because I received a lot. Okay, so here we have y-axis and also x-axis. Okay, we have y-axis and also x-axis. So y-axis, so remember y-axis is the dependent variable, x-axis is the independent variable. Okay, so our y-axis here, which is the outcome, is the length of baby. So put length of baby into y-axis. So length of baby is height. Okay, it's height of the baby. And then enter maternal height into x-axis. Okay, length of baby into y-axis, maternal height into x-axis, and then click OK. And then click OK. So now we have a scatter plot between length of baby and also maternal height. Okay, this is the scatter plot. This is y-axis. This is x-axis. This is dependent variable. This is independent variable. Okay, after that, double click this scatter plot and then click this one. Add fit line at total. Okay, and then click close. Okay, close. Okay, this is the regression line. So this is, we call it regression line. Okay, so here we want to check for linearity assumption. So here you have, here we can say that our data is linear. There is linear relationship between length of baby and also maternal height. So you can see this is, we call it positive linear relationship. This is positive linear relationship. So this is positive, this is negative. If you have, if let's say, the shape of the plot is either U or N, or we call it concavity or convexity. So it means that the linearity assumption is met. So you have to make sure you have this kind of shape. It's either positive linear or negative linear. So this is example of non-linear relationship. Or another example, you have U shape or N shape, your scatter plot. Okay, the next one is the homoscedasticity, which is equivariances. So here we want to make sure the residual, so remember residual, okay, is scattered. Okay, is scattered. So here, go to analyze, go to regression, and then go to linear. Okay, again. After that, go to save. Okay. Under predicted values, click unstandardize. Under residual, click unstandardize. Okay, click unstandardize for both. Go to continue. Okay, go to OK. Once you click OK, you go to data view. At the last column, we have two more variables added. So this one is actually the predicted values. This is residual values. So these values is actually coming from the regression equation. Y equal to B0 plus B1 x1, or Y equal to A plus BX. So since mother's height just now, which is the independent variable, is statistically significant, so we can come up with a regression equation. So length of baby equal to 15.33, okay, plus 0.22 times mother's height. This is independent variable. This is dependent variable. So how to get predicted value? Okay, how to get predicted value? So now we are going to enter the value for the mother's height here. Okay, look at mother's height. Look at mother's height in the data set. Okay, if we added 162 into the equation, so we will get the length of baby 50.97. So even though in the SPSS it calculated 15.7965, but it's fine. It will be slightly different than manual calculation. But this is how we get the predicted value. It's from the regression equation. So we added the mother's height one by one. Okay, and then we will get the value for the predicted. For the residual, so remember the formula for the residual or error, okay, observed value minus predicted value. So in this context, the length of baby. Residual equal to observed length minus predicted length. So observed length here, okay, the observed length here is actually our actual data. Our actual data, which is 56 minus predicted length, okay, predicted length, okay, 50.79650, and then we get 5.2. So this is how we get residual. All right, this is how we get residual. So SPSS calculated predicted and residual based on the regression equation, and then it added the value and then calculated for us. All right. So to do that, so now we are going to check for homoscedasticity. For remember, for homoscedasticity or equivariances, we use SPYR. So we are going to create a scatter plot between residual and also predicted values. Now go to graph, go to legacy dialogs, and then go to scatter or dot, and then click define. So remember SPYR. So remove these two variables from y-axis and x-axis. Okay, SPYR. So x-axis, okay, enter predicted. For y-axis, enter residual. SPYR. Okay, remember SPYR. And then click OK. Okay. This is the scatter plot between residual and also predicted value. So here we want to make sure the spread of the residual here is consistent. So to do this, to check for this, so you double click the scatter plot and then click add fit line, add a reference line to the y-axis. Okay, click close and then close this one. Okay, so this one you have to look for whether there is a pattern like this. So this one we call it convergent or divergent pattern, or we call it fan shape pattern, the Chinese fan shape pattern. If there is pattern like this, so it means that assumption for homoscedasticity is met. But this one we don't have pattern for divergent or convergent pattern. Okay, so it means that the homoscedasticity assumption is met. All right. So this we call it homoscedasticity or equivariances. Okay, the next one, normality distribution of residual. So to do this, we have to create a histogram for the residual, and then we have to see whether there is a bell-shaped curve or not. If there is bell-shaped curve, so it means that the residual is normally distributed. If it's not normally distributed, then if there is no bell-shaped curve, it means that the residual is not normally distributed. Okay, to do this, go to graph, legacy dialogs, and then go to histogram. And then enter residual into variable, and then click display normal curve. Okay, click display normal curve, and then click OK. Okay, here we can see we call it bell-shaped curve. If there is bell-shaped curve like this, it means that the residual here is normally distributed. So the assumption is met. Okay. So now we already checked 3 assumptions for homoscedasticity, linearity, and also normally distribution. So all assumptions are met. So what happens if the assumption is not met? What happens if one assumption is not met? Or what happens those 3 assumptions is not met? Actually, we have many things that we should do. First, what you can do is you can do data transformation. Okay, you can do data transformation. You can transform your outcome or your dependent variable. Or what you can do is you can try to reanalyze again, try with different variable, or maybe you can try to do you can try checking your data whether there is any outliers or missing data or not. But I advise you check again your data and then try to reanalyze again until you get what you want. All right. So once you have checked all the assumptions and then all assumptions are met, so it means that the equation or model that you come up with just now can predict the outcome. Okay. So now we can run the data again. So this is our finding for this. So how to interpret this? So increasing the mother's height by 1 cm will result in 0.2 cm coming from the regression coefficient here. Increase in the length of baby. Or you can say increase mother height, increase length of baby. That's it. That one also fine. So it's up to you. How are you going to do the interpretation? This is actually the detailed way of interpreting regression result. So our regression equation y equal to a plus bx, length of baby equal to 15.33 plus 0.22 mother's height. So when you put in any mother's height, so you can get the length of baby. All right, so this is how we interpret and then come up with the regression equation. Okay, I hope you can understand. So after this, I'm going to focus on multiple linear regression. So the reason we did simple linear regression first is because when we do multiple linear regression, you still have to do simple linear regression. Okay, in regression analysis, we actually have many types of analysis. We have multiple linear regression, we have multiple logistic regression, multinomial, ordinal logistic, cost professional, and so on. So we have many types. So multiple linear regression can be used when you have more than one independent variable, and your dependent must be numerical. For logistic, your dependent variable is categorical, and then that categorical must have two categories only. We call it dichotomous or binary, yes, no. Okay, for example, yes, no, we only have two categories, right? So that one, we call it, you can use multiple logistic regression. Okay, multinomial logistic regression is actually the extension from multiple logistic regression. Dependent variable for logistic, multiple logistic, we only have two levels, but multinomial, we have more than two levels. But these levels or category is polytomous or nominal. So it means that the order of category is unordered. For example, type of diseases. Okay, type of diseases we have, for example, tuberculosis, diabetes, dengue. Okay, these three is unordered categories, so it doesn't matter which one comes first. All right, ordinal logistic is also extension from multiple logistic and multinomial logistic. So the difference is that the outcome is categorical, more than two, and ordinal. It must be ordinal. For example, disease severity, we have mild, moderate, and severe. So mild, moderate, severe is ordered category. It's ordered category. Okay, that one you can use ordinal logistic regression. But I'm not going to cover this multinomial and ordinal now. Okay, I'm going to cover multinomial in the next workshop. But today I'm going to cover only multiple linear regression and also multiple logistic regression. All right, so now please open the second handout that I shared previously. We are going to do multiple linear regression. You can close the data set. We are going to use the same one, but I'm going to make sure everything is clean. We are going to use a new one. All right. So now, let's do multiple linear regression. So let's see any question. Why is it calling length of baby instead height of baby? I mean, that one is up to you. That one is up to researcher how to name your variable. All right, so it doesn't matter height of baby or length of baby, so it's the same thing. Okay, you can change to height if you want. That's not a problem. All right. Okay. So now I'm going to focus on multiple linear regression. Multiple linear regression is used if you want to estimate the relationship between two or more independent variable and one dependent variable. So your dependent variable, which is the outcome of your study, must be numerical, and then your independent variable must consist of two or more numerical variables only. Okay, I repeat again, your dependent must be numerical, your independent must consist two or more numerical variables only. So what happens if your independent variable is a combination between numerical and categorical, or you only have categorical variable only? So we call it general linear regression. So the steps almost the same with multiple linear regression. Okay, the step almost the same, but I'm not going to focus on general linear regression today. I'm going to focus on multiple linear regression only. Okay, let's see the differences between simple linear regression and also multiple linear regression. So remember, in simple linear regression, we only have one independent variable. Our outcome is numerical. Our independent is numerical. For example, okay, our outcome is length of baby or height of baby. It doesn't matter. Okay, independent variable is the mother's height. So here we want to see the relationship between mother's height and also length of baby. Okay, the second one, multiple linear regression. The different multiple regression and simple linear regression is that we have more than one independent variables, and then these variables must be numerical. So here at this stage for independent variable, it's up to researcher. It's up to you which variable that you want to choose. You cannot ask anyone else. You need to ask yourself which variable that you want to include as independent variable. So this variable can be taken from your data set. So you can choose any variable that you think might be associated with the length of baby. So it's up to you. All right. So for example, in this case, we have length of baby as the dependent variable, and then we have mother's height, mother's weight, and also age as the independent variable. So when to apply multiple linear regression, so same concept with simple linear regression. The reason we do multiple linear regression is we want to see the relationship between the dependent variable and also independent variable between two or more independent variable, and then at the same time we want to make the prediction of the dependent variable based on the independent variables that we have, and then eventually we can come up with a regression equation or regression model. Okay, for your information, regression equation or regression model can only be created if the independent variable is significant. If the independent variable is not significant, you cannot even come up with a regression equation. Okay? Okay, this is the multiple linear regression model. So just now, what I mentioned to you, y equal to b0 plus b1 x1. So here, for multiple linear regression, we have more than that. It's longer than that. Why? It's because we have more than one independent variable. So it depends on how many independent variable that you have. Let's say if you have 3 independent variable, so it means that you can stop until B3 as 3. Okay, so y here is the outcome. So I remember someone asked me to repeat the equation just now. Okay, so y is the outcome or the dependent variable. Okay, B0 here is the intercept, the value of y where x equal to 0. Okay, so the B1, B2, B3 until Bn here is the value for the regression coefficient. Regression coefficient for every independent variable. X1 until Xn here is the list of independent variable that we have. For example here, okay, we have mother's height, mother's weight, and also age. So means X1 mother's height, X2 mother's weight, X3 age. Okay, but it depends whether the p-value is significant or not later on. So this can only be created if the p-value is statistically significant. So in multiple linear regression, we have 6 steps altogether. So the first one, you have to start with descriptive statistics, where you have to explore your data. You want to see the overview of your data, the characteristic of your subjects, of your participant. You can see percentage, you can see mean, okay, numbers. And at the same time, you can also do data cleaning. You can see whether you have missing data or not. If there is missing data, what is supposed to do, whether it is error, or maybe the subjects forgot to answer the question. Okay. After that, you can do simple linear regression, or we call it univariable analysis. It's because we only have one independent variable. So at this stage, we have to do simple linear regression for each independent variable that we listed just now. So once we do simple linear regression, we choose which variable, that has p-value less than 0.25 or is clinically important. We choose the value and then we add those variable into multiple linear regression. We call it multi-variable analysis. So I'll explain this further later on about each of the steps. So once we do multiple linear regression, we check whether there is any multicollinearity or interaction effect in the model. Okay, once we check and done, at this stage, we already established preliminary final model. So once we did multicollinearity and interaction, we check all the assumptions. Once all the assumptions met, we already established the final model. The model can be used to predict the outcome. And then the last one, you can do data presentation, prepare the tables nicely, and then do presentation. All right. Okay, just give me 1 second. Okay, now please open dataset birth weight. All right, please open dataset birth weight. Close the one that we did in simple linear regression and open it again. Okay, this dataset contains information on newborn babies and their parents admitted in hospital Kuala Lumpur. A researcher is interested to determine the factors that are associated with the length of baby. So our research question here, what are the factors that are associated with the length of baby? So first, remember, every research question or your research objective, first what you have to do is you have to list down all the variables that you have. And then you have to make sure the variable that you have, that you listed, also available in your data set. All right. And then for your information, you can do anything with your data set. I mean, for example, you can also do grouping. Let's say for age is a numerical numbers, right? You can convert into age group. So it's up to you, right? You have freedom to do what to do anything with your data, to do any modification, but don't cheat. All right. So here, first list down all the variable. So we have factors, okay, factors, which is the independent variable, and then we have length of baby. So the outcome here, length of baby, because we want to see the factors that are associated with the length of baby. So the factors here, which is the independent variable, is depends on the researcher. You need to ask yourself, what are the suitable independent variable, okay, that you think might be associated with the length of baby. You need to ask yourself. You don't ask anyone else, but you don't have any idea, you can also refer to previous study. You cannot ask statistician to decide for you, so you need to ask yourself. So here I would like to choose mother's age, mother's height, and also mother's weight, because I think these three independent variable might be associated with the length of baby. Okay, so once you have come up with the variable, you have to identify the type of variable. So the length of baby is numerical, mother's age, height, and weight also numerical. You can make sure you check with your data set. And then here, the right statistical analysis that you can use is multiple linear regression, because the length of baby here, which is the dependent variable, is numerical, and then all the independent variables also numerical. So you can use multiple linear regression. Okay, now the first step is descriptive statistics. Okay, in descriptive statistics, the reason we do descriptive statistics is because we want to see the characteristic of our subjects. Okay, we want to see the percentage, mean, and at the same time, we want to perform data cleaning. We want to see whether they are outliers, missing data. For categorical data, okay, so now you go to analyze here, you go to descriptive. For categorical data, you can choose frequency. For numerical data, you can choose descriptive or explore. For categorical, frequency. For numerical, you can use either descriptive or explore. So the difference between descriptive and explore, descriptive is just a very simple information. For example, you want to see mean, standard deviation, mean, and also minimum, maximum number, you use descriptive. But if you want to know more information, for example, confidence interval, you want to know interquartile range, okay, you go to explore. So now I'm going to run frequencies for categorical data because I want to see the characteristic of my subjects. Okay, go to analyze, descriptive statistics, and then go to frequencies, and then enter categorical variables. So here we have okay, here we have smoker, enter smoker into variable. We have low birth weight, and then mother's age. So enter these three variables, these three categorical variables into the box: smoker, low birth weight, and also mother's age. And then click OK. And then you see here we have tables. We have frequency table for each categorical variable. We have frequency percentage. We have 20 non-smoker, 47.6%, 22 smoker, 52.4%. Okay, we have low birth weight and also mother's age over 35. Okay. And then later on, you can prepare a table and then prepare a table nicely, and then you can add all the categorical variable and together with frequency and percentage. So usually for categorical variable, we are interested with frequency and percentage. That's why this is the reason why we don't copy this table and then put in our manuscript or our thesis, all right? So we have to create a separate table for it because we don't need every information in the SPSS. Okay, the next one, I'm going to run descriptive statistics for numerical data. Okay, to do this, go to Analyze, Descriptive Statistics, and then go to Descriptive. So here you have option. You can go to Descriptive. You can go Explore, all right? Okay, I'm going to choose Descriptive. And then you can enter all numerical variable. So to select variable at once, you can click Control. You can click Control and then you select the variable. Select the numerical variable. And then enter these variables into the box. And then click OK. Okay, this is the descriptive table for numerical variable. So we have n, and here is the frequency, the number of cases in every variable. We don't have any missing data. We have a minimum value, maximum, we have mean and standard deviation. So you can see which one is relevant to your study. But most research projects usually always put in mean and standard deviation. So it's up to you. If you think minimum and maximum are something that you want to report, then go ahead, you can report it. So it's up to you which information that you think is relevant. All right. Okay, so the second step is simple linear regression. This is what we did just now. Okay, in the first step, which is simple linear regression. Here at this step, you have to perform simple linear regression analysis for every independent variable. So remember, we have mother's age, mother's height, and also mother's weight. So here we have to perform simple linear regression analysis one by one. And then we look at the p-value with less than 0.25 or clinically important. So many people ask me, why we use p-value 0.25? Why not 0.05? The reason we use 0.25 first, okay, is recommended, suggested by epidemiologists and senior biostatisticians worldwide to use p-value 0.25. And the second one, because this is actually the initial stage of multiple linear regression, and we want to allow more variables. We want to allow more variables to be added into the analysis. If you want to fix 0.05, it's not a problem. It's up to you. But if you want to use 0.05, you will only allow just a few variables only. All right. So this is the beginning stage of multiple linear regression. So we want to allow more variables to be added. We don't want to miss any important variable. Okay, now we are going to conduct simple linear regression for each independent variable. So to do this, go to Analyze, okay, go to Regression, and then go to Linear. All right, go to Linear. Okay, first, we are going to perform simple linear regression for mother's age. So remember, our dependent variable is length of baby. So enter length of baby into dependent variable. Okay. Enter mother's age or maternal age into independent variable. And then go to statistics. Then go to statistics, and then please make sure, so I forgot to put in the slide, so you have to take confidence interval. Okay, you have to take confidence interval here, and then click continue, and then click OK. So remember, the most important table that you have to see is coefficient table. So look at the p-value. This is the p-value. So the p-value is less than 0.05. And it is also less than 0.25. Means you will add this value into the next steps of analysis, right? And the second one, we're going to perform simple linear regression for mother's height. So maternal age, significant already. We are going to include this. And then we are going to do mother's height. So to do this, same step as just now. You can just go here. Okay, recall recently used dialog. So you can just go to linear regression. Right, so this is the shortcut, so you don't have to go to analyze regression every time. And then remove maternal age from block 1 of 1 and then enter maternal height into the box. And then click OK. Okay, look at coefficient table. So the p-value for the maternal height is also significant because it's less than 0.05. And we will include this into the next analysis because the p-value here is less than 0.25. All right. Okay, next one is mother's weight. Click linear regression. Remove mother's height from block 1 of 1. Enter mother's weight into block 1 of 1. Mother's weight. Okay, mother's pre-pregnancy weight. And then click OK. Okay, look at the coefficient table. Look at the p-value. So the p-value is 0.009. Okay, it's significant. And then it's also less than 0.25. So we will include this variable into analysis. So now you can also prepare a table for the simple regression. And then you can see here the p-value, all p-value are statistically significant. And then all p-value are also less than 0.25. Okay. What if p-value more than 0.05 but less than 0.25? Yes, you can include. You can include into the next analysis, which is multiple regression. I'm going to show you later. Okay. The next one, so we are going to add these three variables into the next analysis. Okay, this is teaching data set. It will be very different when you use your own data set. When it comes to real data, it will be very different, right? So this is teaching data set. That's why you can see very nice p-values. All values are significant. So don't, I would say, do not, so whenever it comes with real data set, it will be very different. I suggest you can try doing. Don't try doing it one time only. Try to play around with your data until you get what you want. So next analysis is the multiple regression. We call it multi-variable analysis because it involves more than one independent variable. So from previous analysis, we are going to add these three variables, right? So at this step, you are going to analyze by using methods such as forward, backward, and also stepwise. So you have to perform all these methods, and you have to select the model with all variables significant as the preliminary main effect model. Okay, so you have to do for every method here, forward, backward, and also stepwise. So to do this, go to regression again, go to linear regression again. Now we are going to enter all the significant variables that we chose previously. Mother's age, mother's height, and also weight. Weight, age and also height. All right. So now we are going to do forward, backward, and also stepwise method. So to do this, you go to method here, the method here, and then go to forward. We're going to do forward first. Go to forward. Okay, forward method. Okay, you go to coefficient table. So how SPSS carry out forward method? So forward method is at first SPSS will start with empty, we call it empty model. Okay, empty model. And then in the model one, SPSS added the most important variable. So here the most important variable that has been added is age. So you look at here, the p value is significant. And then in the second model, SPSS added additional value, which is mother's height, and then it is also significant. And then mother's weight has been excluded from the model. So means that if you means that in the forward method, mother's age and also mother's height found to be significant, found to be associated with length of baby. Right? So this is forward method. So we're going to do another two methods. We're going to compare. Okay? So now, let's do backward method. So go again to linear regression. Okay, go to linear regression again, and then change forward to backward. Change forward to backward. Okay, click OK. So let's see how SPSS carry out backward method. So look at coefficient table. So for backward method, first SPSS start with full model. So it added all variable at the same time, and then SPSS remove the unimportant variable from the model. So you can see here in model 1, all variables have been added, okay, even though it's not statistically significant. So in the second model, SPSS remove mother's weight from the model, and then you can see that mother's age and also mother's height found to be statistically significant in backward method. So we refer to the last model under coefficient. So in backward method, mother's age and also mother's height found to be significant, found to be associated with the length of baby. So now we can see forward and backward, same result, right? So now we're going to do stepwise method. So go to regression again. We change backward to stepwise. And then click OK. Okay, go to coefficient table. Okay, for stepwise, how SPSS carry out stepwise method? So stepwise method is basically the combination between forward and also backward. So as you can see here in the model 2, mother's age and also mother's height found to be statistically significant. So now mother's age and mother's height actually found to be significant in all method, forward, backward, and stepwise. So now we can see that we already established preliminary mean effect model. Okay, so now go back to linear regression, and then you remove pregnancy weight, mother's weight from the model, and then make sure you only retain age and height, and then method you change to enter. So this is what we call preliminary mean effect model, because we already remove the variable that is not significant. All right. For at this stage, SPSS exclude a p-value less than more than 0.05, not 0.25. The reason we use 0.25 at the beginning is because we want to allow more variables to be added. That's it. Okay, we want to allow more variables to be added, and we want to reduce bias. All right, but SPSS for multiple linear regression step, by SPSS will include especially exclude will only include the p-value less than will only include the p-value less than 0.05. All right, because at the same time we don't want to miss any important variable initially. So this is the reason why we use current point p-value 0.25 in the beginning. Okay, now we already established preliminary mean effect model, age and height found to be associated with the length of baby. Now we are going to check for multicollinearity. So multicollinearity occurs when independent variables in the regression model are correlated. All right, these two independent variables correlated. So multicollinearity can only be done if you have more than one significant independent variable in the previous stage. So let's say when you did forward, backward, and stepwise, and then you found only age found to be significant. So means you only have one independent variables, right? Then you can skip multicollinearity step and also interaction step later on. Okay. For this, it can only be checked if we have more than one significant independent variable. So here we want to make sure the independent variable are not correlated to each other. So to do this, we have to use variance inflection factor, so VIF. So VIF is used to detect the multicollinearity. If the value of VIF is more than 10, so it means that there is multicollinearity exists among the independent variable. Okay, to do this, go to regression analysis again, linear regression, and then go to statistics, and then click collinearity diagnostic, and then click continue, and then click OK. Okay, go to coefficient table. Look at last column. We have VIF. So if the value here is more than 10, so it means that there is multicollinearity among the independent variable. So what you have to do? So means you have to remove the independent variable. Okay, you have to remove the independent variable from the model because you don't want to get inaccurate result. All right. So here the value of VIF here is less than 10, so it's okay. So the value of VIF for both variables are less than 10, so means there is no multicollinearity problem in this model. Okay, the next one is checking interaction. So similar with multicollinearity, interaction can only be checked if you have more than one significant independent variable because it involves more than one independent variable. Interaction effect occurs when the effect of one variable depends on the value of another variable. Okay, so these two independent variables must be biologically meaningful. Means it should have meaning. Okay, so first you have to compute the interaction term in SPSS. So once you compute a new variable, okay, the interaction term, then you have to add the interaction term as independent variable into the model. Then you have to check whether the interaction term is significant or not. If the interaction term is significant, then you can consider to add the interaction term as part of your independent variable into the model. Then you have to check whether the assumption is met or not. So you have to compare model with interaction, model without interaction, and then check the assumption whether both both assumptions met or not. If there is one assumption is not met, then you have to choose another one. All right. So first, you have to compute the variable. All right. So now we have age and also height only. So we have age and also height. So we are going to create interaction term between age and also height. So to do this, go to transform and then go to compute variable. We are going to create the interaction term. We are going to create a new variable, right? So in the target variable, okay, write age underscore age underscore and then height. Okay, we are going to name a new variable. Make sure you don't put space. It's either you make it closer or you put underscore, right? So in the numeric expression, enter age, okay, and then click star here, the star, and then enter height. Age time height, and then click OK. So you look at your data set, last column, we have a new variable created for the interaction term age and height. So now we are going to include this interaction term into our model and then see whether it is significant or not. So to do this, you go to regression, linear regression again. Go to linear regression and then we add the new interaction term that we created and then enter it into the model and then click OK. If you have a lot of significant independent variable, means you have to create more than one interaction term and then you have to test it one by one. You cannot include the interaction term at one time. Okay, so once we added the interaction term, you can see that the p-value of the interaction term is not significant. So means that you cannot add this interaction term into the model. So we will exclude this interaction term. So you go again to linear regression and you remove this interaction term and then you click OK, right? So the interaction term age and height is not statistically significant, because the p-value here is more than 0.05. Now you cannot create an interaction term for 3 variables, so you have to create for 2 variables. So you have to create one by one. Let's say we have one more significant, right? Weight, age, height, and weight. So you can do age and height, you can do age and weight, or you can do height and weight. So this interaction term must be meaningful, must be related. Let's say height and weight. You think height and weight is not related, so you don't have to create interaction term. So those interaction term must be meaningful. For multicollinearity, you just check for VIF. Okay, you don't have to run, you just check for VIF. Check for VIF. If VIF is more than 10, if VIF is more than 10, so it means there is multicollinearity. If VIF is less than 10, so it means that there is no multicollinearity in the model. If there is multicollinearity exists, it means that you have to remove the variable. So you have no choice, right? If it's not significant, if interaction term is not significant, means you cannot include this into the model. So you have to exclude the interaction term from the model. So you cannot interpret the interaction term anymore. Okay, now we already checked multicollinearity, interaction term. Now we are going to check assumption. So in multiple linear regression, we have 5 assumptions. 4 assumptions to be checked during analysis, 1 assumption just during data collection. So first, for overall linearity, we have to create a scatter plot between residuals and also predicted value. So we use rule of thumb XPYR. So X predicted, Y residual. For homoscedasticity or equal variances, we create a scatter plot between residuals and also predicted value, similar as linearity, XPYR. And then we have to do linearity of each independent variable. So since we have two significant independent variable, so means that we have to create a scatter plot for each independent variable. Scatter plot of residual versus each independent variable, xi, yr. X-axis, you put independent variable, y-axis, residual. And the last one, residual should be approximately normally distributed. So this one, you can use histogram to create, you can use the histogram to create the histogram, and then you see whether there is bell-shaped curve or not. If there is bell-shaped curve, it means that the residual are normally distributed. The assumption is met. Okay, first we are going to check assumption for overall linearity and also homoscedasticity. We can do it together because both are using same scatter plot, residual and also predicted values SPYR. Okay, so to do this, you go to linear regression, okay, and then go to save. Under predicted values, click unstandardize. Under residuals, click unstandardized. Okay. Unstandardized predicted, unstandardized residual. So now we're going to ask SPSS to calculate predicted values and also residual values for us. And then click continue. And then OK. So now you can see in your data, we have two more variables added for predicted and also residual. So remember, these values are coming from the regression equation. So SPSS calculated based on the regression equation. After that, we are going to create a scatter plot XPYR. Okay, to do this, go to analyze. Okay, go to linear regression. Go to a graph, legacy dialogues, and then go to scatter or dot, and then click define. So remember XPYR. So X predicted, enter predicted, YR residual into Y-axis, XPYR. Okay, and then click OK. And then click OK. So you can see here, we have the scatter plot between residuals and also predicted values. Okay, residuals and also predicted values. So now double click this scatter plot. And then click add a reference line to the y-axis. And then close this one. Okay. So we already add reference line. So now we want to see the shape. We want to see the shape of the scatter plot. All right. For overall linearity, we don't want any shape like concavity or convexity, or other word U N. Okay, we don't want any plot like this, N shape or U shape. Okay, so here we can say that there is no concavity or convexity shape. So it means that the linearity assumption is met. So I repeat again, if this one, you just have to see by yourself. If there is a concavity or convexity shape, okay, with a convexity shape, so means that the assumption for overall linearity is not met. So now we don't have any kind of that shape. So it means that linearity assumption is met. Okay. Okay, okay. So next one is for homoscedasticity. For homoscedasticity, you want to make sure the spread of the data, the spread of the residual is consistent. So we look at the whether there is divergent or convergent or fan shape. Whether there is divergent or convergent or fan shape. Okay, it's like this. Okay, it's like this. If there is a shape like this in the scatter plot, okay, if the dot looks like this, so it means that the data is not. It means that there is the assumption for homoscedasticity is not met. Right. So here. So now it's lunchtime over here. So people keep asking me whether I want to go for lunch. Okay, I think I'm gonna take a 15 minutes break. All right. But I just finished this one first, and then maybe we take a break for 15 minutes. So I'm going to just this assumption. All right. So for this one, since we don't have any particular shape of divergent or convergent or Chinese fan, okay, so we can say that the assumption for homoscedasticity is met, right? So the assumption for this is met. So there is linear relationship, and then assumption for homoscedasticity also met. So this is example of non-linear relationship. This is example of heteroscedasticity. All right. Okay, so we're gonna take a break for 15 minutes. And then I'm going to continue again with the next assumption later. All right.
Announcement for dear participants. You can register for our upcoming workshop, paid workshop on mastering regression analysis, a step-by-step guide with SPSS part 2. Dates will be announced later with the registrants. Thank you.
Okay, we are going to just give me a second. Okay, I'm going to proceed with the next assumption that you have to check in multiple linear regression. So the next assumption is linearity of each independent variable. So remember, now we have two significant variable, which is maternal age and also height. So now we're going to create a scatter plot for each independent variable. So remember, linearity of each independent variable should be done by using the scatter plot between SI, YR, residual versus each independent variable. So to do this, go again to the scatter plot. Okay, go to the simple scatter plot, SI, YR. So remove predicted from the x-axis. Okay, remove predicted from the x-axis and then, okay, enter. So we're going to do for mother's age first. Enter mother's age. Mother's age into x-axis. Okay, residual into y-axis, xi, yr, and then click OK. Okay, similar as before, double click the scatter plot, and then click add reference line to the y-axis, and then close this one, and then click close. So here, similar with overall linearity, we don't want to see any convexity or concavity or U shape or N shape. Okay, we want to make sure the dot is scattered. So since there is no peculiar shape, there is no U shape or N shape. Okay, in this scatter plot, linearity assumption is met. So this one for the maternal age. So now we're going to do for mother's height. So go to simple scatter plot again, and then remove maternal age, and then enter mother's height into x-axis, and then click OK. Okay, same as before, double click. Okay, double click, and then click add reference line, and then close, and then close. So here we can see that there is no peculiar shape. There is no concave, there is no convex, right? So the dot is just scattered. So we can say that the linearity assumption is met for this independent variable. Okay, the next one is normality distribution of residual. So now we are going to create the histogram. And now we want to see whether there is bell-shaped curve or not. If there is bell-shaped curve, normally distributed. If no, then it's not normally distributed. So to do that, go to graph, legacy dialogues, and then go to histogram, and then enter residual into variable, and then click display normal curve, and then click OK. So here we have histogram. So this we call it bell-shaped curve. Then we can say that the residuals are normally distributed. So the assumption for this is also met. So now all assumptions are met. Okay, now all assumptions are met. Overall linearity, homoscedasticity, linearity for every independent variable, and then residual should be approximately distributed. So all assumptions are met. So it means that the model that you created, the model that you come up with, can be used to predict the outcome. Okay. So this is our final result. Okay, so to do this, so you just go to linear regression, and then you click enter. That's it. Right? And then you click enter. So run the final model. So all the assumptions were checked and met. No interaction, no multicollinearity, all assumptions. Right? So this is how we display the result for the multiple linear regression. So make sure you also include simple linear regression because we want to see which variables are not included in the multiple linear regression. Okay, so you can also mention there is no multicollinearity detected, no interaction among the independent variables, and then the coefficient of determination. So for coefficient of determinations, it can be taken from the model summary R squared 0.621, which is 62.1%. So this is our final model equation. So length of baby equal to, okay, look at the coefficient table. Length of baby equal to 35.96. This is the constant or the intercept of B naught. Okay, minus here because it's negative, minus 0.28 mother's age plus 0.14 mother's height. So when you add the mother's age and also mother's height, then you can get the estimation of the height of baby or the length of baby. Okay. So how to interpret a multiple linear regression? Okay, so let's do interpretation. So this can only be interpreted, okay, multiple linear regression can only be interpreted if the p-value is significant. Okay, if p-value is significant. So remember, if p-value is not significant, then you cannot interpret the result, then you cannot even come up with the final model equation like this. So you have to make sure the p-value here is significant, then you can come up with the regression equation. Okay, so there is significant linear negative relationship. Why linear negative relationship? It's because the value for the regression coefficient here is negative. So there is a significant linear negative relationship between mother's age and also the length of baby. So for every 1 year increase in the mother's age, and the baby's length is 0.28 cm lower. So this is how we interpret in detail. So it's up to you if you want to interpret like this or not, or you just want to interpret in general, but most people usually interpret in general. They don't want to interpret in detail. Okay, the second one is mother's height. Okay, mother's height regression coefficient is positive. There is a significant linear positive relationship between mother's height and also the length of baby. So for every 1 cm increase in the mother's height, the baby's length increases by 0.14 cm. Okay, this is how we interpret the result, the findings for the multiple linear regression. Okay, for coefficient of determination, what does it mean actually? 62.1%. 62.1% of the variation in the length of baby is explained by mother's age and also height. So this is how we interpret the findings for the multiple linear regression. Okay. Okay, so what happens if the assumption or if the one of the assumption is not met for multiple regression? So what is supposed to do? If the assumption is not met, so what you can do is you can do data transformation. You can transform your outcome or your dependent variable. You can also check for the outliers or any missing data in your data set. But I guarantee you, if you have large data set, the result will be nice. Right? The result will be nice. And then I recommend you, whenever you do statistical analysis, is all about experimenting with the data. You cannot rely on one analysis only. You cannot rely on, you do once and then you do once, settle. No. you have to do more and more until you get what you want. So until you get what you want, you can also modify your data, means you can try to regroup the data into any grouping that you think is relevant, or anything is relevant. So you try many times until you get what you want. Okay, so it's all about experimenting with the data. Okay, the next one, we're gonna do multiple logistic regression. Okay, for any kind of SPSS, you can just use forward. Okay, for during the step number 3 for multiple linear regression, you can just select forward, backward, and stepwise. These three methods is only applicable for step number 3. So other than that, we just use enter method. Okay. Okay, the last data that we use to interpret. Okay, this one is just a typical one. So you just go to linear regression and then put your dependent variable, and then make sure you put in the significant independent variable that we use during step number 3, which is mother's age and also mother's height. And then make sure you change to, and make sure you use enter method. Okay, click OK. So that's it. This is our final results already. This is the last findings that we use to interpret the result. This is the last table that this is the last finding. Okay. Okay, I hope you can understand. Now we are going to proceed with okay, for general linear regression, you can just select for general linear regression because it involves categorical data, right? It involves categorical independent variable. So you cannot analyze as it is. You have to change to dummy variable. So there is step to do it, right? So there is step to do it. Okay, now I'm going to go to multiple logistic regression. Okay, multiple logistic regression is different with what you learned previously in multiple linear regression and also simple linear regression, because the outcome here is dichotomous or categorical. So you want to see the relationship or association between dichotomous categorical variable and independent variable. So simple regression is the univariable analysis where you only have one independent variable, and then your dependent variable must be dichotomous, must be categorical. For example, you have categories that mention yes and no. So yes and no is two levels, right? It's two categories. So we call it dichotomous. Okay, multi-logistic regression is the multi-variable analysis where you have more than one independent variable. But for multiple logistic regression, you can combine between numerical and also categorical variables, so it's not a problem. So it can be the combination between numerical and also categorical variable. Okay, let's see the differences between simple logistic and also multiple logistic regression until multiple logistic regression. So in simple logistic regression, you only have one independent variables only. Okay, for example, our dependent variable is a dichotomous categorical. For example, disease and no disease. So disease, no disease is a categorical, two levels, right? Two categories. And then you have independent variable, which is smoking status, which is also categorical. Okay, in multiple logistic regression, you have more than one independent variable. Same goes with multiple linear. You have more than one. Your independent variable must consist of one independent variable, and then it's your choice. You can choose any variables that you think are associated with the dependent variable. So in this case, we have dependent variable, which is disease or no disease, and an independent variable, marital status, smoking status, and also age. So the reason we use multiple logistic regression is, of course, we want to make the estimation. You want to make the prediction of your outcome based on the independent variable, that you have. So you want to make the estimation. So just now, I introduced you to multiple linear regression model, right? Y equal to B0 plus B1 as 1 until Bn as n. It depends on how many independent variable that you have. For multiple logistic regression, it's almost similar with multiple linear regression. The only difference is that we add log odds. Okay, we add log odds. Why? It's because the outcome here is categorical. We cannot do prediction. We cannot make estimation using categorical data. So that's why we have to transform in logistic regression model. We have to transform the categorical outcome here into log. Then you can make the estimation. So the number of X here depends on how many independent variables that you have. All right. So when you use multiple logistic regression, you always you can see odds ratio like everywhere, OR. Okay. So binary outcome concerned with odds ratio. So it's actually the measure of chance. It's like a probability. It's a probability the event will occur to the probability of the event will not occur. Right? So odds ratio can be calculated to see the relationship between the variable and also the likelihood of an event occurring, or you will want to measure the association between the outcome and also independent variable. So OR, okay, many people ask me what kind of study design can we use for odds ratio. So even though odds ratio is used in multiple logistic regression, but it depends on the study design as well. If you use a retrospective study, if you use a case control study in your research, you can use odds ratio. Okay, it's recommended to use, you can use odds ratio. But if you use prospective cohort study, or you use randomized control trial that consists of prospective study as well, you can, it's recommended to use other risk. Okay, we call it relative risk other than odds ratio. Okay, for cross-sectional, we usually don't report OR, but it depends. All right. So how to calculate odds ratio? Okay, this is example. What is the odds of men to have heart disease compared to women? So here we have a column for those who have heart disease and without heart disease. And we have gender, men and women. So odds ratio is the odd of men having heart disease to the odds of women having heart disease. Okay, we have A, B, C, D. So to get the odds of men having heart disease, okay, A divided by B. So 20 divided by 80. Okay, odds of women, C divided by D. So 15 divided by 85. Okay, here's supposed to be 80. Okay, here's supposed to be 80, right? And then we calculate the odds ratio, OR equal to AD divided by BC. Okay, AD divided by BC, sorry, it's correct already. 20 times 85 divided by 80 times 15, and then we get 1.42. So this is how we calculate OR manually. Okay, for SPSS, you don't have to calculate OR manually because it's already comes with the results. So we have similar with linear regression. We have 6 steps altogether. Descriptive statistics, because we want to explore our data to see the characteristic of our study participants. And at the same time, we want to do data cleaning. We want to see whether there are any missing data, any outliers, and then if there is missing data, what we're supposed to do. All right. And then after that, we have to do simple logistic regression. So similar with simple linear regression, at this stage, we do it one by one. And then we choose the p-value which is less than 0.25. So even though it is, let's say, we get a p-value 0.2, then you still have to include, and then you still have, it's recommended to include the value into multiple logistic regression. But it totally depends on you. All right. After that, once you have chosen the variables for the simple logistic regression, then you can proceed with multiple logistic regression. We call it multi-variable analysis because it involves more than one independent variable. But let's say if we only have one significant variable at this stage, or at this stage you only have one independent variable, then you don't have to do step number 4. Right? So after that, you can check for multicollinearity and interaction term. So once done, you already establish preliminary final model, and then you check assumption. If all assumptions are met, then you already establish final model. And the last one is the interpretation. You are ready to display your result nicely in a table, and then do data presentation, result presentation, and interpretation. Now, please open dataset CAD. Okay, CAD, coronary artery disease. Okay, coronary artery disease. Okay, look at this dataset. We have how many? We have 8 variables altogether. So ID is not variable because it's only a numbering, the ID of the patient. So we have 8 variables altogether. All right. So this is categorical variable. This is categorical because it has categories. This is the CAD, coronary artery disease. So this is actually a large data set. We have more than 4,000 data. This is a very good data. We have more than 4,000 data. Right? This, we call it numerical data. So here, we want to know what are the factors that are associated with CAD. CAD is our dependent variable. So you look at our data set, we have CAD. CAD consists of values no CAD and also CAD, coronary artery disease, and without coronary artery disease. And then factors. When you talk about factors, you're actually talking about more than one independent variable. So the independent variable depends on you. You can decide by yourself which independent variable that you think might be associated with the CAD. So I'm going to include SBP, DBP, cholesterol, age, BMI, gender, and also race in the analysis because I think these factors might be associated with CAD. So you can try, you can play around and see. Okay, so after that, you have to identify the types of variable. So CAD is a categorical variable which is dichotomous because we have 2 levels only, no CAD and then CAD, and then for factors is combination between numerical and also categorical. So the right statistical analysis that you can use is multiple logistic regression because the outcome is categorical and is dichotomous. Okay, now we're going to do descriptive statistics. So the reason we do descriptive statistics is we want to see the characteristic of our subjects. So usually when we write in the result section, we don't go straight away into logistic or linear regression, right? We always start with the demographic. about the characteristic of our subjects, right? So this is the reason, this is one of reason that why we start with the descriptive statistics first. So to do that, first I'm going to split the file. So go to transform. So go to data and then go to split file. And then click organize output by groups and then enter coronary artery disease into the box. So here I want SPSS to split the findings into those who have CAD only and those who without CAD only. So I want to see the characteristic of these two groups separately. Click OK. Okay, now go to analyze and then go to descriptive statistics and then go to frequencies. So remember, you only select frequency if the variables are categorical. So enter gender and also race into variable and then click OK. So here we can see SPSS split the findings, splits the result into no CAD and also CAD. So later on, when you mentioned about the social demographic, you can split the table into those with CAD, those without CAD. For example, among CAD, we have 228 women with 36.7%, 393 men, 63.3%. Those without CAD, we have 1819 women, 44.7%, 2250 men, 55.3%. All right, so this one for categorical variable. Now let's do for numerical. Go to analyze descriptive and then go to descriptive and then enter numerical variable into the box. Okay, enter numerical variable into the box and then click OK. So here we can see the tables, the descriptive table for CAD and then no CAD. For example, among no CAD, we have 4,069. In CAD, we have 629 subjects. Okay, so later on, you can do a separate table for this, mentioning CAD and also no CAD. Okay, now I'm going to proceed with the next step. So this is how we display the findings for categorical and also numerical variable. Usually for categorical variable, we are interested with frequency. N is frequency, number of cases, and also percentage. And then for numerical variable, we are more interested with mean and standard deviation. So you can do like this. You can also combine the table. It's up to you. Okay, depends on your creativity. All right, so now we're going to proceed to step number 2, which is simple logistic regression. But before we do that, we are going to unsplit the file because after this, we don't want to split the findings into CAD and no CAD anymore. So what you can do is you go back to the data, go to split file, and then click analyze all cases. So we want SPSS to analyze everything at the same time. So click OK. Okay, so similar with simple linear regression, at this stage, we have to perform simple logistic regression for every independent variable that we have. So just now we have selected SBP, systolic blood pressure, diastolic blood pressure, cholesterol, age, BMI, gender, and race to be our independent variable. So once we do the analysis, then we have to choose the variable with p-value less than 0.25 or is clinically important. If you think the p-value is not if more than 0.25, and then you think it's very important to be included, and then you think it's associated with CAD, so you can include it because it's clinically important. So that's why I said you can play around. Let's see if you use this variable, so what's going to happen? Is it going to be significant? The model assumption will match. So you can try one by one. Okay, so now we are going to perform simple logistic regression. Go to analyze, go to regression, and then go to binary logistic. Go to binary logistic. Okay. Give me 1 second. Okay, go to binary logistic. We have dependent and also covariate. So this covariate also called independent variable. So our dependent variable is coronary artery disease. So enter coronary artery disease into dependent. And first, we do for gender. And enter gender. Okay, enter gender into the box. So since this independent variable is categorical, so you have to go to categorical and then you enter gender into categorical covariates and then click first and then click change. I'm going to explain about that later. Okay, first and then click change, continue, and then click OK. The reason I click first is because you go to variable view, you can see in gender, you go to values. So the coding is 0 women, 1 man. So if you click first, you are actually making woman, because woman is first, you're making woman as the reference group. So when we do the analysis, SPSS will do the analysis referencing man to woman. Okay, so it depends on you if you want to click first or not. So it depends on how are you going to interpret your data later on. Okay, so once you click OK just now, so the most important table that you have to know is the variables in the equation. Variables in the equation. So we have categorical variable coding. So woman, we make woman as the reference group. We have omnibus test model coefficient. So this one we want to test the significance of independent variable in the model. But this one is just generally, okay, it's just overall testing. Okay, so now look at variables in the equation. Variable in the equation table. This is the most important thing that you have to see. So this is constant. So similar with multiple linear regression just now. So we have constant. This is the value for the intercept. Okay, for the gender of the patient. So look at the p-value. So this is the p-value. So the p-value is significant because it's less than 0.05. And then it's also less than 0.25. So we can include this. So this is exponential. Okay, exponential b here, 1.394. This is actually the odds ratio. Okay, this is the odds ratio, the one that I talked about just now, OR. So how to interpret this? Okay, how to interpret this? So here, I mean, you can follow this one is the details of interpreting logistic regression, a detailed way of interpreting. So if 95% confident interval here does not include 1, so it means that the p-value here is significant and the odds ratio can be interpreted. Okay, so how to interpret coefficient is positive? Okay, here coefficient is positive. There is a significant association between gender and also coronary artery disease because the p-value here is less than 0.05. So men have 1.39 times. So 1.39 coming from the odds ratio. 1.39 times odds of having CAD compared to women. So this is the reason why we make women as the reference group. Because when we do the interpretation, we can do the interpretation comparing men to women, right? Okay, next one, let's repeat for race. Okay, go back to logistic regression. Go back to logistic regression. Remove gender and then enter race. Okay, since race is categorical, so you go to categorical and then you enter race into categorical covariates, and then you can click first and then change. Okay, continue and then okay. Okay, here we have for race, we have Malay, Chinese, and Indian. So since we click first, and change, so it means that we make Malay as the reference group. Okay. So look at the most important table, which is variables in the equation. So here we have this one is Malay, Chinese, and also Indian. So it depends on the category that we created when we entered the data. Malay, Chinese, and Indian. Okay, so now we make Malay as the reference group. So for Chinese here, the p-value is more than 0.05, so it's not significant. For Indian, it's also not significant, 0.05, less than 0.05. And then the p-value also more than 0.25. So you cannot add race into the next analysis. But let's say one of these is significant. One of these is less than 0.25 or less than 0.05. Yes, you still can add it even though one of the category is less than 0.25. But since all the value here are more than 0.25, so you cannot add this into the next analysis. Okay, now we're going to do for next variables, SBP, DBP, cholesterol, age, and also BMI. So to do it, go to Logistic. Okay, remove race. What Asan, which version of SPSS you using? Okay, you can do it now. All right. Okay. Okay, now we're gonna do for SBP. So SBP is numerical. So enter SBP into the box. And then, so since SBP is numerical, so you don't have to go to categorical and then change, right? So just click OK. Or you can go to options and then click confidence interval, CI. continue, and then you click OK. Okay, go to the most important table, variables in the equation. So look at SBP. So SBP here is significant because it's less than 0.05, and that is also less than 0.25. So we're going to include this into the next analysis. Okay, now we're going to do for DBP. Okay, go to logistic regression, remove SBP, enter DBP, and then click OK. Okay, I'm going to do faster because we run out of time. Okay, go to the last table. Okay, go to variables in the equation. So DBP, p-value is significant, and it is also less than 0.25. So we're going to include this into the next analysis, right? Next one, we're going to do for cholesterol. So we have to do it one by one. Remove DBP and then enter cholesterol. Click OK. Go the last table. Look at the p-value for the cholesterol. The p-value is significant. It's less than 0.05 and it's also less than 0.25. So we can add this into the next analysis. Okay, next one is age. Remove cholesterol. Enter age. And then click OK. Okay, last table. Okay, age. Okay, look at the p-value for age. It is significant, it's less than 0.05, and at the same time, it's also less than 0.25, so we will add this into the next analysis. Okay, next one is BMI. Remove age, and then enter BMI, and then click OK. Okay, go to the last table, and look at for BMI. The p-value here is not significant because it's more than 0.05, and then at the same time it is also less than 0.25, so we will not add this into the next analysis. Okay, so this is how we interpret the result for the numerical variable. For example, for the SBP, okay, the p-value here is significant. So remember, the result can only be interpreted if the p-value is significant. Okay, so 95% confidence interval here does not include 1. So coefficient is also positive. There is a significant association between SBP and also CAD. So a person with 1 millimeter mercury increase in systolic blood pressure has 1.03 times higher odds of having CAD. So why higher? So we look at the sign for the regression coefficient is positive. It's negative means lesser. Okay, so since it's positive, then it's higher. So it's up to you whether you want to interpret this way, or you can just say higher SBP, higher CAD, higher chance of getting CAD. That's it. So it's up to you. So it depends on the researcher how are you going to interpret the data. Sorry, for race and gender, you still can take. I forgot to take just now. For confidence interval, you can take actually for every independent variable, you can take a confidence interval. So I forgot to do it. I forgot to do it for race and also gender. Yes, when we do multiple logistic regression, it's very recommended to change. It's very recommended to code your data into 0. Start with 0 and then followed by 1 and 2. It's recommended to do it. Okay, so we have done simple logistic regression. Then you can also present your result nicely in a table like this. So remember, you cannot copy the table and put in your manuscript or put in your thesis. Because my student always do the same mistake, even though I mention it so many times in my class. Do not copy this table, all right, when you presenting your result. So now let's look at the p-value. So now we are going to screen the variable that has the p-value less than 0.25. So we are going to select gender, SBP, DBP, cholesterol, and also age to proceed in the next analysis. Okay, step number 3 is a multiple logistic regression, which is multi-variable analysis because it involves more than one independent variable. So from univariable analysis, we selected gender, SBP, DBP, cholesterol, and also age. Okay, now we're going to perform multiple logistic regression. So remember, during multiple linear regression, I advise you to use forward, backward, and also stepwise method, right? To perform multiple linear regression. So in multiple logistic regression, is recommended for you to use this method, forward likelihood ratio, LR, backward elimination likelihood ratio, LR, forward LR, and also backward LR. So it's recommended because likelihood ratio is used to check for the model fit. It's the reason why we choose forward LR and also backward LR in the first place. So you can read the differences between each of the methods here if you want to know further the differences between each of the method. Okay, for the forward, we have likelihood ratio and also walk, but we are going to select likelihood ratio because likelihood ratio is more for model fit compared to walk. So it means that the removing and also adding the variable into the model based on the criteria of likelihood ratio. So there is a mathematical way how to do these steps, but SPSS already skipped this for you. All right. So now let's do the analysis. Go to analyze, regression, and then go to binary logistic. Okay, we're going to enter the variable that found to be significant or p-value less than 0.25 in the simple logistic regression step. So now you can add a gender, okay, gender, SBP, DBP, cholesterol, and also age. You can remove BMI. Okay, gender, SBP, DBP, col, and also age. So remember for categorical, because we have categorical variable here, so you go to categorical, you enter gender into categorical covariates, and then click first, and then click change, continue, and then you can go to options, okay? You can click confident interval if it's not clicked yet, okay? Click confident interval, and then click. Okay, remember to change the method into forward LR. So we're going to do forward LR first. And then click OK. Okay, look at the variables in the equation. So remember for forward, first, SPSS will start with the empty model first. And then after that, SPSS added. Okay, after SPSS will add the important variable one by one into the model. For example, but this one, because we're using forward likelihood ratio, so the process of adding the variable is based on the criteria of likelihood ratio. So you have to read this further if you want to know more why the reason we do this, but there is a mathematical way of doing this. Okay, first, SPS added as diastolic blood pressure, so you look at the p-value is significant. In the step number 2, SPSS added gender and also diastolic blood, SPSS added gender. So gender also found to be significant. And in the step number 3, SPSS added one more variable, which is cholesterol, and found to be significant. So it means that in the forward LR, gender, DBP, and cholesterol found to be significant, found to be associated with CAD. So other variables, which is age and also SBP. Age and also SBP. Okay, age found to be not significant. All right. So now we already have a model for the forward LR. So now we're gonna do for the backward elimination LR. So to do that, go to logistic regression, and then you go to method, and then you change to backward LR. Okay, change to backward LR, and then click OK. For backward elimination, first SPSS added all the variables all together. Okay, all the variable, and then after that SPSS removed the unimportant variable from the model. So here SPSS remove SBP from the model. So now from this we have gender, DBP found to be significant, cholesterol found to be significant, but the problem is age is not significant. So it means that you cannot choose backward elimination LR. So you have to choose forward because it contains the model that has all significant variable. But for the backward, it also contains the non-significant variable. So we are going to rely on forward LR. So in the forward LR, we have gender, diastolic blood pressure, and also serum cholesterol found to be significant. All right. So go back to logistic regression. Go back to logistic regression, and then remove the unsignificant variable, which is age. Okay, which is age, and also SBP. The gender, DBP, and cholesterol found to be significant, and then make sure you change the method into enter. So now we want to choose forward, right? And then click enter, and then okay. So this is our model with significant variables only. So you look at the p-value here, all significant. So now we already obtained preliminary, we call it preliminary mean effect model. All right. Okay, the next one, how we are going to interpret this. All right. For example, for the DBP, a person with a 1 millimeter mercury increase in DBP has 1.05 times the odds of having CAD. Okay, of having CAD. A person with a 1 millimole increase in cholesterol has 1.15 times the odds of having CAD. And then a man has 1.49 times the odds of having CAD compared to women. So this number here is actually depends on the odds ratio. Okay. So now we already established preliminary mean effect model. Now we are going to check for multicollinearity. Okay, from the model that we did just now, we come out with 3 significant variables: gender, DBP, and cholesterol. So first, we have to check for multicollinearity. So remember, multicollinearity can only be checked if we have more than 2 significant variables. We want to assess which variable correlate highly. So in multiple logistic regression, we can check the multicollinearity by using correlation estimates and also by using standard errors. So you can choose either one. If we don't have cutoff point, how high? We don't have cutoff point for this, okay? But if you have high standard error, for example, you can consider to remove the variable for the model. Okay, to do this, now we are going to check multicollinearity by using correlation estimates. So to do it, go to Logistic Regression again, and then click Options, and then click Correlation of Estimates. And then click Continue. And then OK. So make sure method change to enter. Click OK. Okay, go to correlation metric. So look at correlation metric. Okay, so gender versus DBP 0.08, 0.068. Gender versus cholesterol 0.053. So the DBP versus gender 0.068. So you can see here, all the value here are very small. Actually, we don't have cutoff point to check for the correlation matrix. So it depends on you. If you think the number here is high, okay, is high, then you can consider to omit the variable. But here the value here is very small, 0.068, negative 0.05. So it's very small. So it means that there is no multicollinearity among the independent variable. So now we're going to check the multicollinearity by using standard error. So this one you can just looking at the variable in the equation table. So this is the standard error. So here you can compare the standard error with the regression coefficient. If you think the value here is, when you compare the value is very high, so it means there is multicollinearity. Okay, but this one you can choose either one. You want to choose correlation metric or you want to choose standard error. So here standard error is very small. It's very small, okay? So it means that there is no multicollinearity amongst the independent variable. Okay, now we're going to check for the interaction term, for the interaction effect. So we have 3 independent variables. The interaction effect occurs when the effect of one variable depends on the value of another variable. So this interaction term needs to be biologically meaningful. So we have 3 significant independent variables, right? So we can create gender and DBP, gender and cholesterol, DBP and also cholesterol. So you don't have to do like we did in multiple regression. So we don't have to create the terms. So we just can include it into where we do the analysis. Okay, so we are going to check for the possible interaction term for this. Gender DBP, gender col, and also DBP col. Okay, to do it, so you go to binary logistic, okay, logistic regression. And then on your keyboard, you can click Control. First, I'm going to do for DBP and gender. So you click on DBP, and then you click Control, and then you click gender, and then you click here A times B, and then OK. So once you do it, you go to the variables in the equation. Okay, look at the p-value for the interaction term. So look at the p-value for the interaction term. So the p-value here is not significant. Means you cannot include this interaction term into the model. So now we're going to do for second interaction term. So go back to logistic regression, remove the interaction term, and then click gender, and then click control, and then select cholesterol, and then click A times B, and then click OK. Go to the last table. Okay, look at the interaction term. So the p-value is not significant, so means we cannot include this term into the model. So now we're going to check for DBP and cholesterol. So go to logistic regression, remove cholesterol and gender, and then click DBP, click control, and then click cholesterol and enter it into the model, and then click OK. So look at last table. Okay, look at the p-value for the last table. So this one is not significant. Okay, 0.053. So means we cannot include all the interaction terms into the model. And then you have to make sure to remove this interaction term when you do the analysis. Okay. So now we cannot, so now we already established preliminary final model. So we already checked for multicollinearity. There is no multicollinearity exists. We already checked for the interaction term. There is no interaction term exists. Okay, so now we already established final model. Okay, now we are going to check the assumption whether the model can be used to predict the outcome or not. All right. Okay, we have three things that we need to check for in the multiple logistic regression. So it's very different with multiple linear regression. So in multiple logistic regression, first that you have to check is Hosmer-Lemmerschau test. So we want to check for Hosmer-Lemmerschau test. So look at Hosmer-Lemmerschau. If the p-value is we want the p-value more than 0.05. Okay, we want the p-value more than 0.05 for Hosmer-Lemmerschau test. It means that there is no significant difference between the observed probability and also expected probability. Okay, the second one is the classification table. Okay, for classification table, we want the model to correctly classify the cases. Okay, classify the cases into CAD or no CAD. So here we want to make sure the percentage is more than 70%. Means the model is good. Okay. And then the next one is the ROC curve, area under the receiver operating characteristic ROC curve. Here we want to make sure the area is at least 0.7. At least 0.7. Then the model is considered good to use it for Alright. Now let's check Hosmer-Lemmerschau test. So here we have to check for the p-value. Here we want to make sure the p-value is more than 0.05. So it means that there is no significant difference between the observed probability and also expected probability. Okay, so to do this, go to logistic regression, okay, and then go to options, and then click. You can unclick correlation of estimate because we don't need this anymore. Okay, and then click Hosmer-Lemmerschau, goodness of fit. Okay, Hosmer-Lemmerschau, click continue, and then okay. Make sure you remove the interaction term as well. Okay, look at Hosmer-Lemmerschau table. So Hosmer-Lemmerschau is actually SPSS split the data into, we call it 10 groups on decile. Okay, decile, observed, and also expected. And then it compare the value between observed and also expected. Okay, so if the p-value here is more than 0.05, so it means that there is no difference between observed and also expected. This is what we want. Okay, this is what we want. We want a p-value more than 0.05. So there is no, if p-value 0.214 here, it is more than 0.05. So it means that there is no significant difference between the observed probability and also expected probability. Means the assumption for the Hosmer-Lemmerschur test is met. Okay, second assumption is the classification table. Okay, this one, we want the percentage here to be more than 70%. Then you can consider good. So this one, under Hosmer-Lemmerschur test here in the SPSS, you can see classification table. Okay, look at the overall percentage, which is 86.4%. So since the value here is more than 70%, so it means that the assumption is met. So the model is good to do classification. All right. Okay, the next one is the area under the ROC curve. So the value of the ROC curve is between 0 to 1. So we want the model to be able to discriminate those with CAD and then no CAD. Okay, and then we want the value, we want the area to be at least 0.7. So it means it's good already. Right? So to do this, we have to create predicted value. So go to binary logistic, go to logistic regression. Okay. And then go to save. And then click probabilities. Okay, we're going to create a value for the predicted values. And then click continue. And then okay. So you can see here in your data, we have new variable for the predicted. Okay, this is how, remember the one that I mentioned, how we get a predicted value is coming from the regression equation. But this one we use logistic regression equation. Now we are going to create ROC curve. To do this, go to analyze, classify, and then go to ROC curve. Enter predicted probability into test variable. And then enter coronary artery disease into state variable. And then in the value of state variable, you can enter 1. Okay, enter 1. Under display, you can click with diagonal reference line. And then you can just click OK. So here we have ROC curve. Okay, here we have ROC curve. So look at this is the area. Okay, this is the area. Okay, sorry, I forgot. I missed one step. So you have to click standard error and confidence interval. All right. So this is the table for the area under the ROC curve. So look at the area table, 0.709. So we want the area to be at least 0.7. So this one is more than 0.7 already. Okay, it's more than 0.7 already. So it means that the model can accurately discriminate 70.9% of the cases. So we change to percentage. So it means that the assumption is met. All right. So now Hosmer-Lemmerschur assumption is met. It's more than 0.05. Classification table percentage 86.4%. Okay, it's good already. ROC curve also is more than 0.7. So all assumptions are met. And then final model is achieved. Okay, now we can run the final model again. So we just run the final model again. Okay, so make sure everything is okay. The right independent variable, the right method, and then you just click OK. So this is your final model already. Okay, this is your final model. So variable GBP, cholesterol, and gender are significantly associated with CAD. So you look at the p-value here. Okay, look at the p-value here all less than 0.005. Okay, this is how we present the result for the simple and also multiple logistic regression. Okay, for information, I forgot to put in the unsignificant, those variables that are not chosen during simple logistic regressions, but by right you have to put in all the variables that you choose, and then you have to add it in the simple logistic regression so that we can see which variable that are not found to be significant and not included in the multiple logistic regression. So now we can say that we apply forward LR, and then multicollinearity and interaction term were checked and not found. You can also put in the result for the Hosmer-Lemaitre test, classification table, and also area under the ROC curve. But this one is up to you. Not every researcher actually like to mention all of this when they write their manuscript. But for me, I like to mention all of this because I want to prove, I want to show the proof to the readers that I did all these things, and then the model can be used to make the prediction. If you don't show any of these, right? How your readers know that the model is actually, all the assumptions are met and the model can actually be used to predict the outcome. So that's why you have to mention every of these when writing your manuscript and also during thesis writing. Okay, this is how we do the interpretation. A man has 1.49 times coming from the adjusted OR times the odds of having CAD compared to a woman. Okay, a person with a 1 millimeter mercury increase in DBP has 1.05 times the odds of having CAD. A person with a 1 millimole increase in cholesterol has 1.15 times the odds of having CAD. Okay, this is how we interpret the results. So you can interpret in detail like this, or you can just interpret in general way. So it's up to you. Some people don't like writing in detail like this, but they mention everything in the table. So this is how we come up with a logistic regression model. So remember, we have to put in log. Okay, log is a probability, 1 minus probability, so equal to negative 7.24 coming from. Okay, look at the table in the SPSS, negative 7.24. All right, so you have to put in the constant, the regression coefficient for the constant or the intercept in the model. So plus 0.05 DBP, plus 0.14 cholesterol, plus 0.4 gender. So how to calculate the probability? So you have to put in the values here, and then I think you can use calculator to get the value for the odd, for the log here. All right. Okay, so I think that's all for multiple logistic regression. So I need any questions. I'm trying to going through your message one by one here. Usually for the categories that has 1, 2 category is applicable if you will always see this a lot when the variable has a lot of categories. Okay, when the variable has a lot of categories, yes, it is actually means that you have, okay, for gender here you see 1 here, right? So it means that you have 2 categories under this gender. You have 2 categories. You see, for the numerical variable here, we don't have one because this one is not numerical. It doesn't have categories. Okay, For learning ecosystem, okay, for this participant, okay, for learning ecosystem, this one, how many, is it one question or it consists of many questions under learning ecosystem or learning environment, teaching environment? Or this one, you can use multiple linear regression because you have more than one independent variable. So you want to assess a learning ecosystem which consists of more than one independent variable, and then your outcome is the student achievement. So I think the outcome here is numerical. And yes, you can use multiple linear regression. This one, principal component analysis, is that one is different. That one is actually different thing. It's a different thing compared to regression analysis actually. Okay, sorry. Gender one, is it only for male that related, or it's because it's category, so that's why it you can see the number beside gender. Okay. Okay, for the interaction value, okay, remember p-value of 0.25 is only applicable during simple logistic regression step or simple linear regression step only. Okay, for the rest, you use 0.5. The reason we use 0.25 is because we want to allow more variables to be added for the next step. If we set 0.05 in the beginning, then it will reduce the number of variable to be added. So that's one of the reason why you use current point p-value 0.25. So my advice to you, if doing statistical analysis is about experimenting with your data, you can do any kind of analysis once you have your data set. But of course, you have to answer your risk objective and so on. But you can do a lot than that. You can modify your data, try to regroup according to different kind of criteria, BMI, age, and so on, and then do many kind of analysis. So same goes with a multiple logistic regression and also linear regression. When it comes to real data, of course, everything is different. What I showed you just now is because it's teaching data set, right? So of course, everything looks nice, assumption is met, you have significant variable, you have more than one significant variable. But when you have once you do the analysis with real data, it will be a little bit different. So I suggest usually for the regression analysis, it will be better if you can have large data set. Okay, you can have large data set. If the assumption is not met, you can do transformation. For linear regression, you can do transformation for the outcome. For the logistic regression, you can do transformation for the independent variable that you think has a problem. Okay. Other than that, you can look at for the missing data and also outliers. Okay. So this one is applicable for the assumption that are not met. But once again, I suggest you do it more than one. You do more than one analysis until you get what you cannot rely on one's analysis only. Like I myself, I keep doing the analysis until I get what I want or until I satisfied with the result, right? Okay, so I think that's all for today. that's all for today. I'm very sorry if there are any confusions or something during the workshop today. And then I really hope all of you gain knowledge from the today's session on regression analysis. And then in the next workshop, inshallah, I will cover multinomial and also ordinal logistic regression. Let's see if I can do it at once. All right. So thank you so much for participating. And then I really hope I can see you again soon. Thank you so much.
Now the session is open for Q&A. Participants can raise your hands. If you have any questions, participants can raise your hands. If you have any doubts, you can also ask in chat session. Is there any questions from the participant side? You may ask now.
Okay, for the sorry, because I missed some messages. For the interaction term, if the interaction term is significant, you can consider to add into the model. Okay, you can consider to add into the model. After that, you check for the model assumption. You check whether the model assumption is met or not after adding the interaction term, and then you compare without the interaction term, right? You want to compare electrical consumption between rural and urban area. Which one is dependent? Which one is independent? Electric consumption between rural, I think that one is more like Pearson chi-square, right? I think that one is more like Pearson chi-square because you don't have more than one variable, more than one independent variable, if I'm not mistaken. You want to compare electrical consumption between rural and urban areas, so it looks like Pearson chi-square. I think most of the participants still haven't received the slides. Maybe you can get from the organizer because I already sent all the materials previously. Oh, if you want to use graph from SPSS, you can just you want to use graph and then you want to put in Microsoft Word, right? So what you can do is you can just copy. You can copy this image. You can copy. Can you see my screen right now? Okay.
Yes, doctor.
Okay, now can see or not? Okay, if you want to import, okay, this, for example, this ROC curve to Microsoft Word. So you can just right click and then copy as image. So you just go and then you just paste. That's it. Okay. Okay. Okay, which factor affect electrical consumption? Okay, this one, I think first you need to list down, right? You need to list down all the factors, right? You need to list down all the factors, all the independent variable. if the independent variable is the combination between numerical and categorical, then you can use general. If it consists of numerical variable only, then you can use multiple linear. Okay, okay, I think that's all for today. Thank you very much. Thank you very much. I received a lot of messages saying thank you. Thank you very much for participating today. I'm very glad that I managed to do it for 3 hours. It's not easy to talk for 3 hours. I'm feeling very tired already. And then I have to practice for dancing after this. I have team building tomorrow. All right. So I wish you all have a good weekend. Thank you so much.
Thank you, Doctor, for imparting your knowledge and remarks on the concepts. Your presentation was informative, engaging, and thought provoking. Thank you once again, Doctor.